In this video, we're going to look at some other application problems, this time not dealing with finance, but dealing with some natural sciences, although the problems are going to be very similar to the ones we looked at in the previous video. So first, we're going to think about injecting drug or giving a drug to a patient and think about how much of that drug is in the system at one time. So here we have a patient receives 500 milligrams of an antibiotic each day to treat an infection. This is given as a one-time dose at the beginning of the day. As the day progresses, the amount of the antibiotic in the body decreases by 20% until we administer the next dose of the drug in the morning of the next day. We have this idea that the steady state in which the amount that leaves the body is equal to that of the new dose. And this is going to be what happens in the long run. We'll think about that in part 3. So before we get to that, let's think about how much of the drug is in the body of the patient at different time intervals, after 3 days, after 10 days, and then at the steady state. We're going to do this similar to what we did in the previous video, that we're going to look at the 500 milligrams that's injected today, the day before that, the day before that. So today we have 500 milligrams that is not decreased at all. Yesterday's 500 milligrams has decreased by 20%. And note that we can write this 500 minus 500, 20%, as 500 times 0.8. There's 80% left of that 500 from the day before. So this is today's. This is yesterday's. The day before that, we have 500 times 0.80 squared is what's going to be left. And if we're thinking about 3 days, we need one more term here to the third power. That is 2 days ago. And this is the one from 3 days ago. So total, this is a finite geometric series with S sub n equal to a 1 minus r to the n over 1 minus r. And I should say that actually we don't want this last term here because that would actually correspond to 4 days that we're actually looking at. So we're going to get rid of this, and this is thinking about 3 days total. So ignoring that little part, the total sum is S sub n. If we're thinking about S sub 3, what happens after 3 days? We have A, which is 500, 1 minus R cubed. R, I should say, is this 0.8 cubed over 1 minus 0.8. We're going to have a very similar thing for after 10 days. We're going to have 500, 1 minus 0.8 to the 10th over 1 minus 0.8. And the steady state is what happens in the long run. This is, we're going to look at the infinite series. And note that this is really the same idea as the market stabilization problem in the previous video. If we think about the infinite sum, we have A over 1 minus R, 500 over 1 minus 0.8, or 500 over 0.2. It's equal to 2,500. So this is saying that in the long run, we're going to have 2,500 milligrams of this drug in the body. So how much is in the body right after and right before getting a new dose? Well, right after, or say right before, we have 2,500, and right after, we have 2,500 plus 500 is 3,000, as we're adding 500 to that dose. But as the day increases, in fact, actually, I got that backwards real quick, sorry. Right after, we have our steady state of 2,500. So right before that dose, we have 2,500 minus 500, or 2,000. This is saying that after you have the dose, you're at the steady state that you're going to stay at forever. You're going to lose, at this point, you're going to lose 500 milligrams of the drug each day, which means that you're going to gain the 500 the next day, you're going to lose the 500, gain the 500, now you're at a steady state of 2,500 at the beginning of each, or at the end of each first dose. This is really very similar to the market stabilization idea that we had in the previous video. All right, next we have every day a person consumes 5 micrograms of a toxin during breakfast in some way. Maybe it's what we're eating or whatever it is. And this is going to leave the body at a continuous rate of 2% per day. In the long run, how much toxin is in the body at the end of the day? Well, one thing we have to think about for this problem is the continuous rate. Now we're going to go back to chapter 9 to think about how much leaves the body each day with this continuous rate. So we're going to let y be the amount of toxin from the first day still in the body after t days. So the derivative, we know that we're going to lose 2% of whatever's in the body at that time. So the differential equation is dy dt equals negative 0.02y. And we know the solution to that differential equation is y equals 5e to the negative 0.02t. 5 is the initial value, and then we decrease the 0.02 rate per day. And note that using some algebra, we can write this as 5 times e to the negative 0.02 to the t power, just using some exponent rules. So what this is saying here is that how much toxin is in the body at the end of each day, or at the end of the day? Well, we know that each day we're going to do this. So we're thinking about, we have 5 from today. Yesterday, we have 5, but that decreased. We have e to negative 0.02 to the first power. That was yesterday's 5 micrograms. The day before, we use this formula where t is the number of days. This is 2 days ago, and we just keep on going on forever. And that's how much micrograms are going to be in our body, because we have the ones from today, the ones from yesterday, we have the ones from 100 days ago. It's just a very, very small amount from that. So total, this is going to be an infinite geometric series. We have A is equal to 5, R is equal to e to the negative 0.02, which is about 0.98. So this is going to be equal to A over 1 minus R, or 5 over 1 minus e to the negative 0.02. And that is how many micrograms are going to be in our system at the end of the day, because we have it from all the previous days as well. And this is going to be forever. The next day we're going to have that same amount because we're adding the same amount each time. This is like our steady state kind of idea. Now that we're thinking about differential equations, it's worth thinking about what is the difference between the previous problem and a differential equations problem like we did in the previous chapter. And there is a specific difference, and that is because the person consumes 5 micrograms of the toxin at a certain point, instead of continuously consuming the toxin, like from exposure to the air, we use a series. This is the idea of discrete versus continuous. The discrete example is saying that we add 5 micrograms at a specific point in time into the body. Continuous means that we add 5 micrograms throughout the day at a steady kind of way. It's always adding stuff into the system. And when we have a continuous kind of thing, then we can use a differential equation. So if we did the differential equation thing here, if we added 5 micrograms continuously, we would have dy dt is equal to 5 added minus 0.02 y. Similar to what we did before, we could add that 5 to differential equation. But note that we can't do that in the previous problem because it was a discrete thing. It had a finite number of times we added that 5 micrograms in. It'll be a very similar kind of solution, but it will be different because it's a different kind of problem. So note that we're not going to be using differential equations in this chapter, or if we are, it's just very, very specific kind of things like we did in the previous problem. But note that the idea is very similar to what we did in the previous chapter. All right, back to geometric series. All right, so let's think about another kind of thing. We have, at the end of 2013, world oil reserves were about 1,701 billion barrels. During 2014, about 33.3 billion barrels of oil were consumed, an increase of about 0.08% over the previous year. Assuming yearly oil consumption increases at this rate in the future, how long will the reserves last? So we need to think about how much oil is being consumed at any time. So we know that in 2014, we had 33.3 billion was consumed. In 2015, we say that we're going to increase the amount of consumption by 0.08. So here we're going to have 33.3 plus 0.08 increase of 0.08%. That is 0.0008. In this case, that's going to be 33.3, 1.0008. In 2016, we're going to have a similar kind of thing. We're going to have the amount from 2014, but we're going to increase by 1.0008 squared. And we just continue in that fashion forever. What we're doing here is this is the total amount consumed, so we are going to be adding these values together. So the total amount consumed is a finite geometric series. Sorry, not a finite geometric series, an infinite geometric series Actually, it may be infinite, maybe finite. We're going to take a look at that in the next kind of section we're going to look at, the next question in this example. But this is a geometric series with a equal to 33.3 and r equal to 1.0008. So the question is, how long are these oil reserves going to last? Because of this, we're not going to think about an infinite geometric series. We're going to be thinking about a finite one. And we need to think about what is the value of n. So we know that S sub n here is going to be equal to 33.3, 1 minus 1.0008 to the n power over 1 minus 1.0008. And we want to find out for what value of n is this going to be equal to 1701. And we want to solve for n here. So let's solve this equation for n, and that'll tell us how long the reserves are going to last. It's going to tell us how many terms do we need to add up until we get to 1701 consumed. So first, we're going to take 33.3, 1 minus 1.0008 to the n. It's going to be equal to 1701 times 1 minus 1.0008, which is negative 1.3608. Negative because of the 1 minus 1.0008. All right, we divide by 33.3. Negative 0.0409. We're going to subtract 1, or we're going to maybe add this to both sides. And we're going to add the 1.008 to both sides. And this will give us a 1.0409 equals 1.0008 to the n power. If we want to solve for n here, we can take the natural log of both sides. So we get natural log of 1.0409 is equal to n times the natural log of 1.0008. And we divide. We get n is about 50.1. So this is saying that how long will the reserves last? The reserves will last about 50 years. A little bit more than 50 years. That does it for chapter 10. We introduced geometric series, talk about a lot of different application problems, and that will conclude the course. Thank you.